Hello everybody, this is just a quick few minutes lecture so you can pause where you need to on chapters 14 and 15 for Strength and Materials using the Statics and Strength and Materials book, second edition by Chang. Okay, so we're going to go ahead and get started with chapter 14. The key equation that we're going to use here is, if you look at it, sigma equals mc over I. That's one right here that you see right there. M is going to represent the bending moment. C is going to represent the distance between the neutral axis and the outermost fiber. It's usually 1/2 of the beam, and I is your moment of inertia. The only thing that we're really calculating here that we care about is the stress, the sigma max. Compressive stress is negative and tensile stress is always going to be positive. Okay, now while we're looking at bending moments, if I go back to that, this bending moment M, which we've already calculated in chapter 13, if we go back and look at that, the bending moment, if it has a smiley face, if it's concave up, so if force is pressing on it downward and it's forcing the ends to go up and the center to go down, that means it has a positive bending moment. So that means that the top is going to be in compression and the bottom is going to be in tension. If the beam has a negative bending moment, meaning if it's pressed on from up underneath or being pulled upward, then it's going to have a frowny face shape where the center of the beam goes up and the ends of the beam go down. Then the opposite is true. So keep that in mind when you're working through these things. Now, one other concept that's really important to be introduced here is called the section modulus. Okay, so one thing we definitely want to make sure that we do that, and that's really all the section modulus is I over C. So it's the moment of inertia over the C value. So you'll find that the book does substitute these variables in place for that. So if you take a look at this line right here, sigma max equals MC over I, if we take that C over I, and it's really I over C, and we substitute in the S value, we have M over S. Some section modulus for common shapes are shown here, okay, as I highlight those so you can kind of see what we're doing there. Now, the best thing for me to do is to really go through an example problem with you, so I'm going to do that now. Okay, so if we look at problem number 1 in our textbook in chapter 14, it says that a timber beam that's 10-foot simple span and has a full rectangular section 4 inches wide by 6 inches deep. Figure out what the maximum flexural stress is, sigma, in the beam due to a concentrated load of 800 pounds at the center. So this is the equation that we need to use. Again, M, C, and I. We're trying to find this sigma here. So we're going to use from chapter 13 that simple table on page 473 to find M. So if we take a look, we know that with the center span, case 1 applies. And we do that, we look at that page, we'll find that this formula is the one that we're going to use. Now we have to be careful that we don't forget to change the feet to the inches. And when we do that, we plug in our numbers here. We've got 800 pounds, okay, which we see here. And then we've got the 10 feet span with the 12 inches. Okay, that's the conversion. Okay, and then divide by 4 from the equation, we get 24,000. Okay, so that's the next step. Now, if we go ahead and take a look at it again, we need to find the moment of inertia. Now, the moment of inertia, this is a mistake here. Okay, BH cubed. I need to fix that. I'm fixing that for you now. Okay, if we go ahead and calculate that out, we'll see that we put our numbers in. It's a 4 by 6 beam. Okay, so 4 by 6, base times the height cubed divided by 12, and we have 72. In this case, our height is 6, so that means our C value is going to be half of 6, which is 3. We go ahead and substitute those values in. We substitute that 24,000 in that we found on the previous slide. We substitute in the 3 for C, and we substitute in the 72 that we found just above, and we get 1,000 psi. So that's what we need to do. So these problems are pretty simple. It's a matter of using this equation, the sigma equals MC over I, The M's are going to be pretty straightforward to figure out if we use the chart in chapter 13 on page 473. That should be available to you. Okay, so that should be pretty straightforward. Now, if we go ahead and move to chapter 15, this is a little bit of a backwards chapter where we are going to be shopping for a beam that we need for a given situation. So here we know what we want the beam to do, and we're just trying to find the beam size. So before, what we've done is we've found the stress for a given beam. Here, we need to know, we have the stress, but we have the bending moment, but what we need to do is we need to find the beam that's going to fit our situation. So we're shopping for a beam that's going to work for us. Section 15.3 is all about steel beams, and section 15.4 is all about timber or wood beams. So what we're going to do is we're going to work through an example together to get through section 15.3. Okay, so the first one that we're going to do here is select the, problem number 15.1. We're going to select the wide flange steel section for a 20-foot span that's going to carry a load of 4 kips per foot. Now it tells us to use A36 steel and assume that the beam is supported laterally for its entire length. So it's a simply supported beam. Step 1, this is important, is we're going to determine all the loading conditions, all the conditions including the loads. Now we were told A36 steel, and if you look on page 545, you'll see that those values are given right there. So that's what we need, okay? It's going to have a simple span with a uniform load. So we're going to need chapter 13's table again on page 473. And that's going to give us case 4. Okay, it's a uniform load all the way across the simple span. And these are the other numbers that we need in order to calculate that bending moment. Okay, moving on to the next step. Step 2 is we're going to find the shear force and the bending moment using those formulas from that table in our books. We look at the case that we need, and we have WL over 2 for our shear load and WL squared over 8. We go ahead and substitute our values in from the last slide, the 4 kips per foot, and which is 4,000, and then the 20 feet. And we go ahead and substitute that in, and we get our values of 40,000 pounds for shear, and we have 200,000 pounds per foot. Now we need to change that to kips per inches. That way we can calculate things properly. Okay? All right, the next step is step 3. We're going to use the bending moments and figure the minimum required section modulus, because this is what we're going to be shopping for. Okay? So we've got S equals M over sigma. And if you remember, we had sigma equals M over S before, and we're just solving for S. So we already have our stress that we need, and that's the 24,000. That's right here. Okay. And we just calculated out the bending moment. So we're going to use those two numbers to determine our section modulus. And that's this number right here. We take those two numbers. This one we were given. This one we had to determine using the chart. And then we go ahead and do the math there. We get 100 cubic inches. Okay? That's the number that we're going to use to shop in the back of the book. So we'll have to go to the back of the book where the wide flange beams are. Okay, and then that's the next step. We're going to look at the table in the appendix to try to find that 100 to see what applies. Okay, so in looking at the appendix, I can find these 3 beams right here, the 18 by 60, which has a section modulus of 108, W14 over 84, which is a section modulus of 123, and then the W1468, which has a section modulus of 103. Okay, so any of these according to that situation will be acceptable. So, but what we need to do is we have to do some checks to make sure that we are okay. And one of the checks that we have to do here is right here in this highlighted section. The beam weight to load making sure that we have enough extra section modulus. And if we compare those two and we get this relationship, then we know we're good to go. So continuing on, if we go ahead and do that calculation, if we look up the values in our book, we look up the values in our appendix, and then we go ahead and calculate these out, we can get these values here, okay? And we see that the 0.08 is bigger than the 0.015. Since that is the case, then we know that that condition is satisfied. We also have to check for shear stress here, okay? So we're going to check those sections, and we can go ahead and check with this equation here, substituting our numbers in, and we get these numbers from the sizes in the back of the chart, okay? These numbers here came from the appendix. So I didn't want you to realize or look at that and say, hey, where do we get those numbers from? We got those numbers from the back of the chart, okay? Now, if we go ahead and take a look at this 5284, we had to calculate that. And we're going to compare that to the original value that we had before, that 14.5 KSI, and we can see we're definitely under that, so we know that our shear condition is not going to be a problem. So we can make sure that it's not going to be overstressed, and we can see that it's also not going to snap. So we can say that that first beam that we had selected, 18 by 60, is sufficient for the design. So the one thing I do want to make sure I note is that there's more than one solution for these problems. As long as you're going through the steps and doing the checks, you'll get the problem correct. And it's just really a matter of following the steps, okay? All right, now looking at the timber problems, these are just a little bit different. They're very similar, but they're a little bit different. So step number one is pretty much the same. We're going to determine the conditions in the loading, and that information should be given. Okay. Then step number two, we're going to have to figure out our shear force and bending moment. So we can use the 13-1 on page 473 to help us out. And step three, we need to get our number to go shop with, and that's going to help us out here. Again, that's the same thing. Okay. So this number, this SREQ, is the number that we're going to shop for in the back of the book. We can calculate the minimum cross-sectional area and then do our checks to make sure that that's okay. If you have questions about the timber problems, go ahead and look at the examples that are given in the practice problem solutions, and the examples in the book are also excellent. That should help you figure that out as well. I hope that helps, and let me know if you have any questions. Thanks.